And then I will take questions regarding the first lesson yesterday, which dealt with the unit circle. And then from whatever time we have left until 1:15 is when you'll be working on and asking questions about the second section. So there's a lot of details in this trigonometry section of the course. The first thing that you need to know are the radian equivalence of some very common angles. So the starting point in my mind anyway is knowing that pi radians is the same as 180 degrees. That's kind of just what a teacher would call a math fact. You need to know that. And based on that idea, you can split 180 degrees into chunks depending on whether you're talking about 30 degrees. So for example, if you're talking about 30 degrees, you should understand that a 30-degree slice, I'm going to draw on the screen here, that's one 30-degree slice, two 30 degrees, three 30 degrees, four 30 degrees, five 30 degrees. There are a total of 6 30-degree chunks. And I don't know that you need to necessarily visualize that to know there are 6. I hope I said 6. There are 6 30-degree chunks in 180. You can just say, well, 30 degrees divides into 180 6 times. Anyway, that's the reason why 30 degrees is pi over 6. It's 1/6 of pi. You can do the same thing with 45 degrees. With 45 degrees, there we go. There is one 45-degree chunk, there's a second, there's a third, and there's a fourth, and that means that 45 degrees is pi over 4. When you look at 60-degree chunks, and again, you don't have to visualize these chunks, but it's very helpful for some people. When you look at 60-degree chunks, from here to here is 1, from here to here is a second one, and then there's a third one, which means that there are 3 30-degree chunks in 180. Sorry, 3 60-degree chunks in 180. And that means that 60 degrees is pi over 3. I'm not going to draw this. You can see clearly that 90 degrees is half of 180, so 90 degrees is pi over 2. You need to know these things. Secondly, we worked with the arc length formula. What I don't have on this presentation in terms of review is your ability to convert from radians to degrees, and you need to know how to do that as well by setting up ratios. But the arc length formula is theta equals a over r, and the important aspect of that formula, because after all it's given to you on your formula sheet, there's nothing really to memorize here, but you do have to know that theta has to be in radians in order for that formula to work. A is the arc length, which is the distance along the circumference of the circle, and r is obviously the radius. Theta is the angle between those two arms, between those two radii that determine or define that arc length. We did a lot of review here in terms of Math 20-1. You should know that a rotation angle in standard position always has its initial arm on the positive x-axis. And if it's a positive angle, it rotates counterclockwise. If it's a negative angle, it rotates clockwise. Something that I didn't review specifically in your notes, but it's going to be useful for starting tomorrow, I guess, is the concept of a reference angle. And I'm going to make up angles here. On your screen, you're looking at red angles called theta. And the theta in all 4 of these are rotation angles. So for example, the rotation angle in this particular diagram might be 65 degrees. The rotation angle in the diagram below it might very well be 140 degrees. The rotation angle up here on the top right of your screen might be 240 degrees. And the rotation angle down here in the bottom diagram might be 330 degrees. So all I'm doing is I'm making up angles. The first angle in the top left is in quadrant 1. The one below that, which is in quadrant 2, is 140. in quadrant 3 is 240, and in quadrant 4 is 330. These are just made up numbers. You can come up with any angle you want in that quadrant. We make a big deal here a little bit later tomorrow about what's called a reference angle. And you learn about reference angles in Math 20. The reference angle is defined as the smallest angle from the terminal arm to the x-axis. And it has no real direction. So the reference angle for the first example is this angle here that I'm thickening with the black line. It would be 65 degrees. The reference angle in my diagram below it would be this, because a reference angle is between the terminal arm and the x-axis. So we would do a little bit of calculating there, and you can see that, I hope you can see that what you are going to have to do is take 180 degrees and subtract the 140 to give you the reference angle, because in that diagram the rotation angle of 140 and the reference angle have to give you 180 degrees. In other words, the reference angle in this particular case is 40 degrees, 180 minus 40, 180 minus 140. Up here, I hope you can see that to find this reference angle, what you are going to need to do is take 180 degrees and take it away from 240 degrees, because 180 degrees plus this reference angle would have to give you 240. So I end up getting a reference angle, and I'm just subtracting these in my head, so I'll double check with you in a second, but I get a reference angle of 60 degrees. And down in the bottom corner, what you would have to do is take 360 degrees and subtract the reference angle to get back to 330, or take 360 minus 330 to give you a reference angle of 30 degrees. So just a quick question for you. I forgot to put REF up here. Does anybody have any questions with finding the reference angles in any of these four situations? And secondly, did I do my subtraction right when I had to? Does that look okay?
It looks good.
Okay. Thank you, Aiden. And I don't know who else was talking. I wasn't looking at the screen, but thank you as well. So you're going to need to know that moving forward. And I just thought I would squeeze this in here today because we have some extra time. So then we looked at the unit circle. And the unit circle is defined as a circle of radius 1 unit. So the radius is 1. It's centered at the origin. The equation of the circle is x squared plus y squared equals 1. And the most significant aspect of the unit circle so far, well, I shouldn't say so far because it's going to be the most significant aspect of the unit circle. The most significant aspect of the unit circle, the most important thing, is that anywhere on the unit circle, the cosine of the rotation angle will give you x, and the sine of the rotation angle will give you y. Usually, with the x squared plus y squared equals 1, that's used to determine if a point is on the unit circle, because you need to know that in moving forward to the next thing I want to review, which is the second lesson from yesterday. One more thing. You need to know the coordinates of all of the special points on the unit circle. So, for example, if I ask you, what is the exact value of, we'll just say sine of 5 pi over 3. And you want to know the value of that. I'm going to do a quick little sketch here, and then I'll show you a better diagram. 5 pi over 3, well, here is pi over 3. This is 2 pi over 3, 3 pi over 3, 4 pi over 3. 5 pi over 3 is here. This is 5 pi over 3. You need to know on the unit circle that the coordinates of that point are 1/2, comma, negative root 3 over 2. And I'm not going to, on this page, explain to you why I know that, but hopefully most of you know that by now, even though it's been less than 24 hours since you learned this. When you take a look at the x-coordinate, it is clearly 1/2 of the radius of the circle, and that means y is automatically the root 3 over 2, which means sine of 5 pi over 3 is negative root 3 over 2. So you do need to know the coordinates of all of the points, whether we're talking about the points in quadrant 1, and I'll just review this here, with the 45-degree angle, with the point that is halfway between the two axes, those coordinates are always equal to each other. I don't know what I did there. There we go. Those coordinates are always equal to each other. And you have to, I guess, memorize that they're both root 2 over 2 or 1 over root 2. The oddball angles, which I'm calling them, are the angles that are not in the center. These two always have numbers where one of the coordinates is 1/2 and one is root 3 over 2. So if I want to determine which is 1/2 in this point, I simply draw a line over to the y-axis and I draw a line down to the x-axis, and I ask myself, is this 1/2? Well, no, there's no way it's a half because this is 1. 1/2 is down here, which means the x-coordinate is a half. So the second thing about the unit circle that's very useful is knowing all of these coordinates. And by the way, if sine is the y-coordinate and cosine is the x-coordinate, we have to remember as well, tangent is y over x. And I'm not going to go through this. You have that unit circle in front of you. The goal really is by the time you get to any kind of exam in trigonometry, you just can build the parts of the unit circle that you need when you need them. Okay, and then the last thing we looked at was this new set of trigonometric ratios. I'll show this to you first because this is how I taught it to you. Cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. Again, though, I'm looking here, if cosecant is the reciprocal of sine, then it's also true that sine is the reciprocal of cosecant. These are on your formula sheet, so you don't need to memorize them. There is a way to memorize them. Each pair has one co. There is, in this pair, cosecant and sine. In this pair, there is cosine and secant. In this pair, there is cotangent and tangent. So when you pronounce these, there's a co in each pair. Then, of course, everything is defined in terms of x, y, and r, which is where we left off yesterday. So that's it up till now. Let's take a look now, please, at the questions dealing with the unit circle. So this is lesson 30.4.2, dealing with the unit circle. These questions were on page 186 of your textbook. Take a minute or two, look over your work, and see if there are any questions you would like me to explain or go over from this section. Number 6. So determine one positive and one negative angle that would pass through this particular point. So the first thing that you need to know, Katrina, is where that point lies on the unit circle. Because these numbers are coordinates and they are precise coordinates, they're exact values, they're not weird decimals, the expectation is that we can locate exactly where that is on the unit circle. So I am going to approach this from a standpoint of a student writing an exam. So they're sitting there looking at a sheet of paper. Maybe they forgot to bring their Tim Hortons cup with them so they could draw a nice circle, but they do their best and they draw what they consider to be a reasonable circle. And what they are doing is they're reconstructing the unit circle on paper. That's not bad. It's a little bit lopsided on the top, but that's okay. And I look at kind of dividing this in half horizontally and dividing it in half vertically. So I've got a circle with my quadrants. And this is the unit circle. This is what the student should be thinking, that they're constructing the unit circle, because if it's the unit circle, there's a relationship between the sine and the cosine and all of the angles. Now, we want to locate negative root 3 over 2, 1/2. So the first thing I would say is that since x is negative and y is positive, we're talking about quadrant 3. We're talking about something in quadrant 3. If I told you to plot that point, you would have to measure root 3 over 2 to the left and 1/2 to the right. Now what we want to do is recognize that, I hope everybody knows that on that unit circle that we've constructed, there were 3 points in each quadrant that we cared about. And the middle point is the 45-degree point, I call it, and that's the one where the x and y coordinates are equal. And when you look at the coordinates here of this point, Katrina, they're not equal, which means that this point, I'm going to just erase some things so that I can indicate something with arrows. This point is either here or here. It's one of those 2 locations. So now we need to decide which one it is. And again, I'm just going to start with the top point, and I'm going to extend this point over to the y-axis and extend this point down to the x-axis. Keeping in mind that my circle isn't perfect, the question is which of these 2 coordinates is 1/2? And remember, it's a unit circle, so the distance from here to here is 1. Well, that means that this would be the 1/2. Now, it's negative because it's to the left, but it doesn't matter. And what I've discovered here, Katrina, is that the coordinates of the top point, and I don't really have room to write this, I'll squeeze it in. The coordinates of the top point are negative 1/2 for x, which means y is root 3 over 2. I want to pause there. Forget about the question. Do you see, looking at this and this, how I determine that the x-coordinate of this point is 1/2? Does that make sense to you, how I've determined the x-coordinate is 1/2? Okay, good. So what we've discovered, of course, in going through this process, and I mean, I know some of you would say I'm going too slow here because you get it, but this is really, really important to moving forward. What we have discovered is that this point in the question is not this point. It is, in fact, that point, because you can see the y-coordinate is 1/2, which means the x-coordinate is negative root 3 over 2. So, big deal. So what does that tell us? It tells us that the rotation angle passes through that point. It tells us that we have to rotate this over to here. So the question is now, what could theta be? You should know that this angle, this what I can now call the reference angle, this reference angle is 30 degrees. You should know that because these are 30-degree chunks. And if that's 30 degrees, then I can determine this angle by taking 180 minus 30, so I can write 150 degrees, or I could say it's 1, 2, 3, 4, 5 pi over 6. And if I want another angle, because it said one positive and one negative, I could, if I want to work in degrees, I'll use a different color because it's getting kind of cluttered here. I could say that this is negative 180 to here, plus another 30 in the negative direction gives me negative 210. Or if I wanted to work in radians, this is negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7 pi over 6. So Katrina, have I answered your question? You're welcome. Any other questions before we move on today? Any other questions from the unit circle assignment? All right, so give me a second to open up my other file. So the next thing that we studied yesterday, and we didn't have class time for homework, dealt with the whole x, y, and r thing, and I said that you would have time today to work on that. However, while you're working on it, some of you may have questions. Some of you may have questions right now that you want answered based on that whole x, y, r thing and finding exact values of trig ratios. So if you have no questions, you can get to work on these problems. But keep your ears open because I'm sure some people do have questions. If you do have questions, now's the time to let me know. To be, absolutely, Amy. So determine the approximate value for each trigonometric ratio, and we want to determine the approximate value of the cotangent of 160 degrees. That's the correct question?
Yes.
Perfect, thank you. So what this is making sure you know how to use your calculator. It would be nice if everybody who designed calculators had a cotangent button just like they have a tangent, and a cosecant just like they have a sine, and a secant just like they have the cosine, but they don't. So we need to remember that the definition of cotangent of an angle is it's equal to the reciprocal of the sine of the angle. And what that means, if we cross multiply and rearrange, is that sine of the angle is equal to the reciprocal of the cotangent. I wrote sine, I meant to write tangent, I apologize. I don't know where sine came from. Cotangent is the reciprocal of tangent, and tangent is the reciprocal of cotangent. So how does that help us? Well, cotangent is the reciprocal of tangent. So if I want to determine the cotangent of 160 degrees, I can simply figure out what the reciprocal of the sine of 160 degrees is. These are the same. So when I want to figure out what cotangent of 160 is, I grab my calculator. I make sure that my calculator is in degree mode because the angle is given in degrees. And I take 1 divided by, why do I keep writing sine? I'm really sorry, I'm stuck on sine here. It's tan. Okay. I'll get it together. Cotangent and tan are reciprocals of each other. So I need to take 1 divided by tangent, and this is the answer, whatever I get here. Some people, that doesn't make sense to some people. What some people prefer is for me to say, I'm going to figure out what tangent of 160 is, and then I'm going to say, since cotangent is the reciprocal of tangent, I'm going to take the reciprocal, which is 1 over the number that I got, but you'll get the same thing. to a lot of people, you see that it's the same thing. Anyway, other than my mess up with being fixated on sine, Amy, instead of tan, does that make sense?
That does. Thank you.
You're welcome. Other questions?
Could you do number 5 on the booklet, I guess?
Yep.
Thank you.
So this question, Ava?
Yep.
Okay. I don't know how quite to teach this to you, this idea that I'm going to tell you, but after a while you will recognize certain questions as being an x, y, r question. And if you're given a trigonometric ratio, like we are, cosine of theta equals 4 over 5, and asked for a different trigonometric ratio, it's almost always the case that you're going to take an x, y, r approach. And the reason why that's helpful is the thing we're trying to find, cotangent of theta. Okay, so I know what cotangent of theta is equal to in terms of x, y, and r, but here's the reasoning that you have to go through in your head. Cotangent is the reciprocal of tangent, and you need to know that tangent is y over x. So this is what's going on in my head. I'm figuring out that tangent of theta is y over x, and then I'm saying, okay, cotangent is x over y. That's how I'm going to find cotangent, the reciprocal of tangent. And that means that I need to know x, and I need to know y. Don't use that as an abbreviation on an exam. That's just me cutting some corners. The other thing that is going on in my head is I know that cosine of theta is x over r. It is one of those facts that I need to know. And since cosine of theta is 4 over 5, that's telling me that x is 4 and r is 5. Okay, so I can put that in my list. X is 4 and y and r is 5. So remember, I need to know y. Now I'm going to find y by understanding that the relationship between x, y, and r, so there's all kinds of things going on here. The relationship between x, y, and r is that x squared plus y squared equals r squared. So I can put in 4 for x, 5 for r. Let's do that. I'll have 4 squared plus y squared equals 5 squared. Let's see, 4 squared is 16 plus y squared equals 25. So I figure out what 25 minus 16 is, and I get 9. But don't forget, when you take the square root, you have to go plus or minus the square root. And what that means is that all of this work is telling us y can be positive 3 or y can be negative 3. Now, does that make sense so far, Ava?
Yes.
Okay. Now, when I say y can be 3 or negative 3, I'm not saying you can just flip a coin and pick one. We have to look at the mathematics of the question. And this statement right here, 3 pi over 2 is less than theta, which is less than 2 pi. What does that mean? It means that theta is between 3 pi over 2 and 2 pi. It just means that this is the smallest value of theta that we could have, and not even have because there's no equals to here. And over here to the 2 pi, that's the biggest value. So when I draw this in terms of the coordinate system, 3 pi over 2 is here. I wrote that down wrong, didn't I? Nope. 3 pi over 2 is here, and 2 pi is here. So this is 1 pi over 2, 2 pi over 2, 3 pi over 2. It's between 3 pi over 2 and 2 pi. In other words, Ava and everybody, this is a very fancy highbrow way of saying the angle is in quadrant 4. And for angles in quadrant 4, do a very good job of drawing that. For angles in quadrant 4, x is positive and y is negative. And that means when we were at y equals plus or minus 3, we're going to end up saying, you know what, there's no or to it. Y equals negative 3 because it's in quadrant 4. And then what we can do, now that we know it's negative 3, we can put x, which is 4, over y, which is negative 3, and pick the answer, which is D. Did that make sense?
Yes, thank you.
You're welcome. So continue to work here. We still have about 15 minutes before I'm going to move on. But any other questions? I'm going to continue to do questions while you're working for those that want me to. Okay, I'm here, so interrupt me at any point in time using your mic or typing in chat if you need some help. And then at about quarter after 1 rather, I'm looking at a different computer and the clock is wrong on it. At quarter after 1, we will move on. All right, so we have a point, P of theta. All P of theta means is that the point can be described by saying 3/5 comma some unknown y coordinate, or it can be described by talking about the angle that results in the intersection of that point. Now it is on the unit circle, and that is very important for you to understand. The reason it's on the unit circle is when we take a look at the x coordinate here, which is 3 over 5, we're looking at the cosine of the angle. So the cosine of the angle is 3/5. And there's two ways to approach this, and I'm just going to go with the unit circle approach first, and then I'm going to show you something that I think is easier on the mind. On the unit circle, x squared plus y squared equals 1 because r is 1. So what you do not want to do with this approach is you do not want to think that this is x and this is r, because if it's on the unit circle, r is 1. What you want to do is say that this whole thing is x. There is a way to make the 5r that I will talk about in a second. So if we want to find the y coordinate, which is what question A says, we can put 3/5 squared plus y squared equals 1. And you know what, Jenna? In retrospect, looking at what I've done here, I could have just said that from the beginning. I didn't even need to talk about cosine, but I chose to. Okay? So now we're going to figure out what that is. And I suppose what you could do is just use your calculator. I'm going to do that rather than using exact values because I'm just interested in what I get for y squared first. I'm going to have to take 3 divided by 5, which is 0.6. I'm going to have to square that, and then I'm going to have to take 1 minus that number, 1 minus x squared. So what I get, and I'm going to convert it to a fraction now, is y squared equals 16 over 25. Now, if y squared is 16 over 25, that means y is equal to plus or minus the square root of 16 over 25. And we lucked out. It doesn't always happen, but we get y equals no radicals. We get positive 4/5 or negative 4/5. And then we're going to do the same thing here that I did with the question that Ava asked about. Well, which is it? You're told that P of theta is in quadrant 4, and if it's in quadrant 4, then y is negative. So in this quadrant, which is quadrant 4, x is positive, and 3/5 is positive, and y is negative, which means it's not positive. The value of y is negative 4/5. Now, how do we determine everything else? So far, what we have is x equals 3/5. Y equals negative 4/5. And since we took the unit circle approach, r is 1. If you were asked for the value of tangent, then tangent of theta is y over x. And I want you to pay careful attention to how long I drew that line for the part that separates the top of the fraction from the bottom. I don't want to do something like this. It becomes very unclear where the fractions are if you do that. So I'm going to multiply the top and the bottom here by 5, which can eliminate those mini denominators. Right? So what happens is these two 5s cancel and these two 5s cancel, and you're left with negative 4/3. So tangent of theta equals negative 4/3. What else are we asked to find? We're asked to find cosecant. Now, cosecant of theta is the reciprocal of sine, and sine is y over r, so it's r over y. But since it's on the unit circle, r is 1, so it's the reciprocal of y. So the first question I have for you, Jen, is, does that make sense? Does that help?
Yes, that helps.
Okay. What you could do, everybody, is say, you know what, I'm not going to use the unit circle. And I want to be careful here because I know it says it's on the unit circle, but I'm going to draw the unit circle here. There it is. This is 1, and the point is here. So this is the arm. But the fact of the matter is, I'm actually going to make that circle a little bit smaller. The fact of the matter is, what I can do is I can make that circle 5 times larger and talk about this point. So rather than using a radius of 1, what I can do is use a radius of 5. I like this better. And if I use a radius of 5, it's still the same angle, but now cosine is 3/5, but even though it's on the unit circle, I equate this with x and this with r. And then when I calculate y, I don't get a fraction, I just get negative 4. And it will all work out the same. Let's take a look at number 3 in the booklet. Again, it's this x, y, r thing. The thinking here, the kind of pattern that we see, is that if you were given one trigonometric ratio and asked to determine another trigonometric ratio, you want to take the x, y, r approach. Now, luckily, this isn't on the unit circle. The thing with points that are on the unit circle is we get all kinds of weird fractions for x and fractions for y. The first thing we want to do is equate secant of p with x, y, and r. And by the way, Lauren, p is just an angle. It could be theta or r, or it could be any kind of angle letter you want. So what goes on in my head is I say to myself, secant of an angle and cosine of an angle are reciprocals. So I don't need to write a formula here. I could take that approach, but all I'm saying is, what's the relationship between secant of theta and some other trig ratio? So that's the first thing that goes on in my head. Then I have to say that cosine is x over r. And what that means is that secant is r over x. So cosine is x over r. We need to know that. And secant is the reciprocal of cosine. We need to know that. So when we put those two ideas together, we get r over x. And here's what we can do now. Because this number 2 is not a fraction, we can turn it into a fraction of 2 over 1. And what that means is that r is 2 and x is 1. So what I'm doing here, Lauren, is I'm equating the top of this with r, and I'm equating the bottom of this with x. Does that make sense so far?
Yes.
Perfect. So now, how do I find sine? Well, sine of an angle is y over r. So another fact we need to know. All of these facts, these x, y, r's, and reciprocals, they're floating around in our head, and we've got to be able to grab onto them. So what we are missing here is y. If we knew y, we could find sine, because then we would know y and r. I need to find y by using x squared plus y squared equals r squared. So I will have 1 squared plus y squared equals 2 squared. Let's see, that will give me y squared equals 4, which is 2 squared minus 1, which is 1 squared. So y is equal to the square root of 3. Now it could be positive square root of 3 or negative square root of 3. So now we need to go on a little hunt to figure out which it is. When we look at the question, it says, this one's pretty easy, it's in the first quadrant. If the angle's in the first quadrant, then all of the coordinates are positive, which means that y is root 3, and that means we get root 3 over r, which is 2. So the answer is root 3 over 2. Is that helpful?
Yes.
Perfect. Okay, everybody, we are going to move on now. We are only covering one lesson today, though. So you may still have some questions from this section that you need to practice. And there's still an opportunity tomorrow to go over any questions that you want. 4.3 part 2. So what we were just talking about with the whole XYR thing is section 4.3, trigonometric ratios. And we're also covering 4.4 part 1. I'm not sure why your textbook did it this way, but the second half of section 4.3 and the first half of section 4.4 are exactly the same thing. What these two sections deal with is solving trigonometric equations. So this is what we're working on today, solving trigonometric equations. And we're going to solve them over a specified domain. You'll see what that looks like in a minute. And we're going to solve them over a domain of every real number. You will notice here that the type of trigonometric equation we are solving today is what I'm calling basic. So the trigonometric equations that we're solving today could be considered basic, which means that tomorrow we're looking at something more complicated. Okay. So to begin with, let's look at a very simple statement that says sine of theta equals 1 over 2. Warm-up number 1 says show that 30 degrees makes that statement true. So what are we asked to do here? We're asked to show that sine of 30 degrees is 1/2. Well, I don't know what I need to write here. I guess from a maybe junior high standpoint, I could show that by going to my calculator, making sure I'm in degrees, and my teacher says, Paul, show me that sine of 30 degrees is 1/2, and I go, ta-da, there you go. Sine of 30 degrees is 1/2. And then my teacher says, okay, show me that 150 degrees makes this statement true. And I go, okay, well, sine of 150 Yeah, it makes it true. At this level, what we would probably do is we would probably, on a unit circle, draw in 30 degrees and say to ourselves that the coordinates of that point are, well, let's see, one of these numbers is a half and one is root 3 over 2. Looking at this top number, the y coordinate, you can see it's a half, root 3 over 2. So at this level, you would say, or I would say to my teacher, well, sine is the y coordinate, and the y coordinate at 30 degrees is a half on the unit circle. And 150 degrees also has a y coordinate of a half. So that's how I would demonstrate that the sine of 150 degrees is 1/2. I don't think we really need to write anything here. The important point is that they're both equal to the same thing because they have the same y coordinate. And we'll formalize this answer, which is the answer to C, in just a second. But these have the same y coordinate, so they're going to have the same sign. Now, why do they have the same y coordinate? They have the same y coordinate because this reference angle and this reference angle are equal. Any two rotation angles that have equal reference angles will have the same numbers for x and y. They may be positives of each other or negatives of each other. It depends on the situation. So in order to answer this question, y is sine of 30 equal to 1/2 and sine of 150 equals 1/2. Well, it equals 1/2 each because, first of all, both angles are above the x-axis. Why is that significant? Because the sine of an angle is related to the y coordinate. So if the terminal arms are above the x-axis, they both have positive y coordinates, which means the sines are both positive. If you're missing that because you're writing, what I've just done is I've highlighted the fact that these are both positive numbers. And that is the reason why we say both angles are above the x-axis. But why are they both equal to 1/2? Like, why is the number the same? Well, that's the second point to be made. They have the same reference angle. So, the fact that the numbers are the same is the reason that leads us to this statement. So, the sine of 30 is a half, and the sine of 150 is a half. Those two sines share two things in common. They have the same sign. What I mean by they have the same sign is I mean they have the same sign. They're both positive. Okay? The other thing they have in common is the values are the same. So not only are they both positive, they're both equal to a half. And the two reasons I've highlighted are the reason why they have those two things in common. We're going to end up using that to solve trigonometric equations. But before we do all rotation angles coterminal with 30 degrees make the statement true? We'll think about this for a second. I'm going to go back to my diagram. There's 30 degrees is the green angle, so I'm going to draw another green angle that is coterminal with 30. It ends here. Will it still have the same coordinates? Absolutely. What about another green angle that is coterminal with 30? How about this one? Well, that's coterminal with 30 because it ends in the same place. Basically, because coterminality involves landing at the same point and the sign is the y coordinate of that point, it doesn't matter how you get there. And the same could be argued for 150 degrees. So the answer to this question is, yep, they have to. Now, what does this mean and how is this related to what we're learning today? What it means, when you take a look at this equation, and this is the most important outcome of our warm-up, that equation has two different locations that make it true. One of the locations is here, and one of the locations is here. So that equation has two different locations that make it true, and each of those locations has an infinite number of angles to get there. So that equation has an infinite number of solutions. All right, now I'm going to review something from grade 11. Oh, one last thing. Write the general statements. We're writing statements that make sine of theta equal to 1/2 true. Well, theta equals, let's stick with degrees, 30 degrees plus 360 degrees times n, or 150 degrees plus 360 degrees times n. You might notice that I didn't put plus or minus, I just put plus. And for that reason, for both of these, I'm going to say that n is an integer. Integers are positive and negative whole numbers and 0. Okay, I'm going to pause there. Any questions with anything we discussed in the warm-up, specific to A, B, C, D, and E, or general? Any questions? All right. On the grid below, write the word positive or negative in each blank. Now, we have done this in Math 20. Well, I don't know. I did this with my Math 20 students, so I can't guarantee that all of the Math 20 teachers did this. But what I want to do is go through this process to find out if you understand how to determine if sine, for example, is positive or negative in quadrant 4. Well, sine is always y over r. And in quadrant 4, y is a negative number. R is always a positive number. And what I'm saying is I think that you should be able to think about it for about 5 to 10 seconds when you need to and say, in quadrant 4, sine is negative. Let's do sine in quadrant 3. Well, in quadrant 3, y is negative, r is always positive. So when you take a negative divided by a positive, you get a negative. And what I would say to you is that sine is negative when the angle is below the x-axis. I wish you could see my arms because what I would do in class is I would say to you, I would be facing you, so here's me. And I would have my arms here and here, and as I'm talking to you, what I would be saying is that y is negative, I hope this works, y is negative down, no, y is negative, really? I think I got it now. Y is negative, nope, down here and down here. I was hoping I could move both my arms at the same time, but I can't. So y is negative down in this quadrant, which is quadrant 3. I would be facing you. Y is negative down in this quadrant, which is quadrant 4. So I would tell you that since sine is connected to y, sine is negative in those two quadrants. I would then take my arms and I would rotate them up. I would say, well, where is y positive? Well, y is positive up here, and y is positive up here. And that means that for sine, sine will be positive in the upper two quadrants. I can't judge your faces here, and this is an important idea. Does anybody have any questions? Does that make sense so far? Okay, I'm going to assume that it's all okay. Now, when I talk about cosine, I stand facing you in the classroom with one arm up and one arm down. And I say, where, and it's going to look really funny, where is x positive? And by the way, I really hope that you get the idea that this is the set of axes. So where is x positive? And you'll have to imagine me doing this. I take my left arm and I move it this way, and I say in this quadrant is where x is positive, and I also take my other arm and I move it this way. So what I end up doing is standing in front of you and holding both of my arms like that, and that's where x is positive. Why do I do that? Because x is related to cosine, and that means that you should know that cosine is positive in quadrant 1 and quadrant 4. And I think I'm through trying to demonstrate with my arms through a cheap animation. If I were to move my arms into this quadrant where x is negative and into this quadrant where x is negative, I would discover that cosine is negative there. Tangent is a little more complicated. Tangent is y over x. So in quadrant 1, x and y are both positive. So if you take a positive number for y in quadrant 1 and a positive number for x in quadrant 1 and divide them, you get positive. In quadrant 3, y and x are both negative. So when you divide a negative by a negative, you get a positive. In quadrant 2, y and x are oppositely, I wanted to say charged, but I'm thinking physics. They have opposite signs in terms of SIGN. When you divide them, you'll get negative, and the same will be true down here. So I'm going to pause there. Does that make sense, everybody? This is not something, that's a bad question to ask when I can't see your faces. This is not something we memorize. What I want to know is if you think you feel comfortable in determining the quadrant that an angle would be in if I told you whether sine or cosine or tangent is positive or negative. So any questions with that at all? All right, so now we're going to move on. Solve this trigonometric equation. Now we are in radian mode. Cosine of theta equals 0.5240. The only way you can find out the solution to this is to first of all determine what is called a reference angle. And the reference angle will be found by taking the inverse cosine of what the cosine is equal to. I'm sure you remember this from grade 9, maybe, but definitely grade 10 and 11. The only thing that's going to be awkward here, everyone, is we are in radians. And the reason that is going to be awkward is you will not recognize the angle. It will not look like a nice angle. So we want to make sure we're in radians. And we're going to take inverse cos of 0.5240. And this is what I mean. The angle is 1.02 radians. Now, if I told you it was 68 degrees, then you would go, that makes sense. But this is in radians, so we're not entirely clear as to how big that is. So theta reference equals 1.02 rads. Now, the thing that we are trying to find, which is theta, is not the same as theta reference. Okay? When you use your calculator, you're finding a reference angle, not the angle in the equation. The angle in the equation is called the rotation angle. So now what you do is the following. You draw two separate grids, because you're going to need to look at some pictures here, and you ask yourself, which two quadrants can the angle be in? Well, there's a positive here. We didn't write it, but cosine of theta was equal to positive 0.5240. So cosine of theta is positive, which means theta must be in two particular quadrants. I want everybody to take a second and identify the quadrants that they will be in. So if I were standing in front of you, I would be taking both of my arms and shifting them to the left, because in quadrant 1, to my left, in other words, over here and over here, in quadrant 1 and quadrant 4, x is positive, x is related to cosine, so cosine is positive. And now what we do is we draw the reference angle in each of those quadrants. Again, everybody, these terminal arms, I'm going to clean that up a bit. These terminal arms indicate where theta has to end. So theta, I'm going to write theta in green. Theta will be this in quadrant 1, and theta will be this in quadrant 4. So if you have a reference angle in quadrant 1, theta is simply that reference angle. You can see that this rotation angle, theta, and this reference angle are the same angle. When I take a look at the one in quadrant 4, I need to take this angle, which is 1.02 rads, away from a full revolution to get theta. A full revolution is 2 pi. So I need to take 2 pi and back off 1.02 rads to get that green rotation angle. And that tells me that the angle for the second position is theta equals 2 pi minus 1.02. And I figure out what that is. I'm allowed to work in decimals here because of all of the decimals given in the question. I think it probably also says to the nearest hundredth or something. So 2 pi minus the answer, Nope. Do that again. Gives me 5.26. Can I get somebody to confirm that that's the other rotation angle? Oh, nearest 10th. Thank you, Emily. 5.26?
Yep.
Good, thank you. So the two angles would be 1.0 and 5.3 rads to the nearest 10th. And those are the only angles between 0 and 2 pi. So, how do you solve a trig equation? You use your calculator or some other method to find a reference angle. You draw the reference angle wherever the rotation angle could be. Then you figure out the rotation angle. Let's try one more. Cosecant equals this number. Well, we can't go inverse cosecant, but we can change this to sine of theta equals the reciprocal of this number. So sine of theta is equal to negative, and this is one of the rare cases where I'm just going to put the negative out in front, of 1 over 1.658. Now, we've got a domain of degrees. So do me a favor, put your calculator in degree mode. And then, and it doesn't matter whether I'm in person with a class or explaining things like now, people are going to miss this important point. We're in degree mode. And we're going to go inverse sine. But when you find a reference angle on your calculator, it is absolutely crucial that you never put a negative in. This negative here is not used in finding the reference angle, okay? Ever. Your textbook tries to work itself around how to use that negative, and I wouldn't look at that. It's confusing. So what is the reference angle? It's the inverse sine of 1 divided by of 1 divided by 1.6588. By the way, there's no need for you to calculate what 1 divided by 1.6588 is. That's irrelevant. When we hit equals, I'm obviously not in degree mode. When we do that, we get 37 degrees, 37.1 degrees. The reference angle is 37.1 degrees. Okay. Now, in which two quadrants do we draw this? Well, now we do look at that negative. This is my eyeball. I'm looking at the fact that sine actually was negative. So where is sine negative? It's negative where y is negative. So it's negative here. This is 37.1 degrees. And it's negative here. This is 37.1 degrees. I don't know if you've noticed, but when I draw a reference angle, I don't draw arrows on the arc. A reference angle has no direction. So what I would like everybody to do is use your calculator to figure out how many degrees this is, which is a rotation angle, and figure out how many degrees this is, which is a rotation angle. So for the top angle, I'm going to take 180 plus 37 degrees, Well, 37.1. And for the bottom one, I would take 360 minus 37.1. How was my addition and subtraction there? Do you get the same answers?
Yes.
Thank you, Aaron. Thanks, Chloe. Thanks, Patrick. Thanks, Sarah. Thanks, Keith. So, two-step process. Find the reference angle. Well, three-step. Find the reference angle, sketch the reference angle in the appropriate places, then figure out the rotation angle. Again, this angle is called the rotation angle, and it's this and this that we've determined. Let's try another one. Tangent of theta plus root 3 equals 0. Now there's a little trick to this question. The first thing you have to do is rearrange it for tangent. And you get tangent of theta equals negative square root of 3. The tough thing here, everybody, is we want exact values. And I haven't met a whole lot of students who can figure out the exact values when it comes to tangent by looking at a unit circle. And we want angles in radians. So here's what we're going to do. We're going to find a reference angle by taking the inverse tangent of root 3, no negative. But, well, let's try it. Let's put our calculator in radians. And find the inverse tangent of the square root of 3, and we get 1.047 radians. Now, we can't figure out what that is as an exact value. If you try to convert it to a fraction by going to your math menu, it doesn't do it. And the reason is that number is a multiple of pi. Now, if I told you that that number was pi over 6, let's just check something out. Pi divided by 6, I guess I'd be wrong. Pi divided by 3, I think it is. Pi divided by 3. Well, it's pi divided by 3. But you would never know that. So here's how you cheat. You say, I'm not going to recognize the angle if it's in radians, so I'm going to put it in degrees so I know the exact value. Inverse tan of the square root of 3 is in fact 60 degrees. So what you've done is you've said, in a cheaty kind of fashion, theta reference is 60 degrees. Oh, that means you write down on an exam that it's pi over 3 because you should know 60 is pi over 3. Second step, I would like everybody to identify the two quadrants that tangent could have a negative value. Remember, tangent is y over x, so they have to be opposite. One has to be positive and one has to be negative. And that occurs here in quadrant 2 and here in quadrant 4. Now we can draw in the reference angle. Well, it's pi over 3. So what are the rotation angles? What is theta and theta as exact values? So you might want to look up here if you're not sure. The first theta would be, I'll use a different color here, This time I will use that god-awful pink. The first theta is 1, 2 pi over 3. The second one on the bottom of the screen is 1, 2, 3, 4, 5 pi over 3. This is why you need to be able to count off those angles properly. So theta is 2 pi over 3, and theta is 5 pi over 3. Any questions with C?
I have a question.
Aiden, is that you?
Yeah.
Okay, go ahead.
So when you found that the tangent of negative root 3 was pi over 3, would we ever have to do that algebraically and like show how we found it?
No.
Okay.
That goes to, if I gave you, let's just look at something else. If I gave you cosine of theta equals negative root 3 over 2, you should be able to, and this isn't even an algebraic thing, you should be able to determine with knowledge of your unit circle that those are the two places where cosine is negative root 3 over 2. So the first question I have for you, Aiden, is do you see why cosine is negative root 3 over 2 at those locations?
Yeah.
Okay. The idea is if it's the root 3 over 2, the other piece is a half, and clearly the y's are going to be a half. Earlier I said I have met very few students who can look at the unit circle and tell me where tangent is. Now I do happen to know that tangent will either be 1 here, root 3 here, and 1 over root 3 there when you divide y by x. But no, you don't have to worry about that. You can always cheat with your calculator by, as I've said before, if you have a written response question, whoever's marking it doesn't know how you got from here to here. And there's no work to show in either case, whether you're using your calculator or a unit circle. So no. Are you okay with that?
Yeah.
Okay. Let's take a look at D. Here is one that's going to piggyback on the conversation that Aiden and I just had. When I rearrange this equation for sine of theta, so I can start to talk about a reference angle, I have to add root 3 to both sides and then divide by 2. Now, forget everybody about a reference angle approach, okay? Don't worry about a reference angle approach. I'm going to tell you that if you know your unit circle, you can get the answer to this in about 10 seconds, whether it's in degrees or radians, because on the unit circle, sine is y, and root 3 over 2 is the bigger of 1/2 and root 3 over 2. That is, and this is a really lopsided circle. I'm going to just repair it a little bit. Root 3 over 2 for y, sine is y on the unit circle, is here. Oh, 60 degrees, 120 degrees. I am done. If you know your unit circle, you get the answer to this question in as long as it takes for you to either visualize or draw it. So I'm going to put the answers of 60 degrees and 120 degrees down here. And now let's try it with a reference angle approach. So I'm not going to be checking with everybody on this, but what I want you to do is have your calculator in degree mode and find a reference angle. The reference angle will be the inverse sine of root 3 over 2. And hopefully in the time that I've been writing that, you have figured out that the reference angle, when you're in degree mode, is 60 degrees. Can I get a couple of you to type yes or confirm that verbally?
Yes.
Good. Perfect. Thank you. Now you say which two quadrants is sine positive, and you say, well, it's positive wherever y is positive, which is quadrant 1 and quadrant 2. So what are the rotation angles? 60 degrees, 120 degrees. If you know your unit circle, though, you can get the answer very quickly. Any questions with D? All right. We're going to omit E. And to be honest, I think even if we were in school, my plans on this unit changed so that I wouldn't worry about E. And we're going to omit F. And the reason we're omitting them is because they have goofy domains. The domain for E is from negative 3 pi over 2 to 2 pi. And the domain for F is from negative 180 to 180. I normally teach that for a calculus reason, for calculus-bound students, but I teach it in calculus now anyway. So, we have one last thing we want to look at, I believe, which is example 2. It says the general solution to a trig equation is a statement that includes all of the angles that are solutions. So, I want to back up, and you don't need to go back in your notes. I'm just going to go back here to what we wrote about our warm-up. You remember that the equation in the warm-up was this equation, sine of theta equals a half. And I told you that theta equals 30 degrees was a solution, and we confirmed it on the calculator. And I told you that theta equaled 150 degrees was a solution, and we confirmed that on the calculator. But then I talked about the fact that 30 degrees happens to be this location, 150 degrees happens to be this location. By the way, they both have a reference angle of 30 degrees, and they are in the quadrants where sine is positive. So what we said was the general solution is 30 degrees plus multiples of 360. And 150 degrees plus multiples of 360. That's all example 2 is asking us to add on to our answers. So when we look at example 2, it says for A, B, C, and D in example 1, what's the general solution? Can I get somebody to confirm that in example 1A, we got these two angles that were between 0 and 2 pi?
That looks right.
Okay, so that means the general solution is that plus 2 pi n, and this plus 2 pi n, where n is an element of the integer sets. That's all we have to do to come up with a general solution. Over here, for example B, our solutions were 217 and 323 degrees. So we add multiples of 360. I don't really have room, but for both of these, I'll squeeze it in. N is an element of the integers. Same thing here. And over here, 2 pi over 3 plus multiples of 2 pi. And 5 pi over 3 plus multiples of 2 pi. I hope it's obvious that when we've got answers in degrees, we add multiples of 360. When we have answers in radians, we add multiples of 2 pi. Because 2 pi radians, which is a full revolution, is exactly the same as 360 degrees Okay, just a note now, before I get a little bit of feedback from you. I do not want you doing any questions that have messed up domains, like this one. Negative pi to 3 pi over 2. If you want to try that as a challenge, that's fine. But I don't want you, I'm not going to be going over any of them. So 5b is out. C is out. Man, these are all out except for A. Well, that makes your life a little bit easier. Again, if you want to see if you can figure them out, you can, but I don't want to go down that rabbit hole. Now, tomorrow we're going to be continuing with this, so it's really important that you understand the procedure. Find a reference angle somehow. If you use your calculator, do not use negatives. Once you have the reference angle, identify the quadrants that the angle could be in based on this. Based on your knowledge of X, Y, R, and the quadrant system. Once you've drawn the reference angle in the two appropriate quadrants, figure out by hook or by crook, however you can, what the rotation angle is to get there. And finally, if you were after a general solution, then all you do is you take your answer and you add multiples of 2 pi or 360. So give me a quick feedback here on the content from this lesson. Too fast? Too slow? Just right. And then you can get to work on that. We will go over any questions you have tomorrow. And in addition to that, of course, if you have questions between now and 2:30, which is the time you're expected to be here until, go ahead and ask. And at 2:30 you can take off, or you can hang around until 3. So I'm done yapping. You can get to work now. Let me know if you have questions, okay? Sorry, Sarah. Yes, I can do 3b. I don't know why my chat speaker doesn't indicate anything. So 3b is a weird question. Cosecant of theta is undefined. So we can't use our calculator to find a reference angle. We have to kind of weasel and maneuver our way around this question by using other things that we know. So we know that cosecant of theta in this particular question is equal to, well, it's not defined. Now, how can something in mathematics not be defined? I just want to check here, Sarah. You're with me on this? Okay. So how can, and I apologize for not noticing the question earlier. How can something in mathematics not be defined? Well, there's a number of different ways, but in terms of trigonometry, not defined occurs because you're dividing by 0. When you divide by 0, that's not defined in mathematics. Now, why can we divide by 0? When you take a look at the definition, everybody, of cosecant of theta, so again, I go through this process in my head. I say cosecant is the reciprocal of sine. That's something I know, and that's something I hope that all of you know, but if you don't, it's pretty easy to look on your formula sheet that sine and cosecant are reciprocals. And sine of theta is y over r, which means cosecant is r over y. So now the question becomes, where is y 0? Because if y is 0, it doesn't matter what r is, that will give you your undefined. So y is 0. I'm just going to go with a unit circle, although it doesn't have to be a unit circle. Y is 0 in this location and this location. If it's the unit circle, the coordinates of this point are 1, 0. If it's a larger circle, the coordinates of this point might be 10, 0. But what is important is that the y coordinate of both of these points is 0. And that means that any angle that takes us there is a solution to the equation. By the way, this is another thing that makes this difficult or confusing. The reference angle here is 0 degrees. So one of the solutions is 0 degrees. One of the solutions is 180 degrees. Is 360 degrees a solution? Well, no, because it says theta can be equal to 0 degrees, and it can be up to 360 but not equal to 360. So because this thing here is missing the or equals to, we wouldn't say 360 degrees is a solution. So the two solutions are 0 and 180. Does that make sense, Sarah? Perfect. So this just has a little wrinkle in it with number 5, everybody. Once I show you the first step, I think you could probably finish it. But what we're going to do is treat this equation the same way we would treat the following equation. If I had 3a minus 1 equals 4a, and I said solve for a, then you would subtract 3a from both sides and get, I'll actually write this, and get a equals negative 1. Well, the fact of the matter is, though, it's not a that 3 is being multiplied by, and it's not a that 4 is being multiplied by. I just want to rewrite this. It's 3 cosine of theta minus 1 equals 4 cosine of theta. So we're going to start by subtracting 3 cosine of theta from both sides. And what that's going to leave us with is 1 cosine of theta equals negative 1. Now, there's a bit of a problem here. Does that make sense so far, Aiden?
Yeah.
Okay. There's a bit of a problem here, and we've already encountered it with Sarah's question about the one where I think cosecant was undefined. And the problem is this. Basically, whenever you have the locations that are in any of these 4 positions, the concept of a reference angle is kind of a crappy one, particularly if it's these 2 locations. These 2 locations that I've double circled have a reference angle of 0. The other 2 locations have a reference angle of 90. But we can go ahead and still try this with our calculator. If cosine of theta equals negative 1, the reference angle is the inverse cos of 1. Remember, we don't put in any negatives when we do that. And I believe that when you take the inverse cosine of 1, you are going to get 0. Am I right?
Yeah.
Okay. So the reference angle is 0. And then here's where things get really twisted. Are we in degrees here? Radians. So 0 rads. Here's where things get really twisted. Cosine is negative. And that means that you were talking about quadrant 2 and quadrant 3, where cosine is negative. Now imagine, I just want to work in degrees because it's just a little bit easier. Imagine instead of this, forget about this question, but I told you the reference angle was 20 degrees. Then you would draw the following two things. Does that make sense?
Yeah.
Okay, but the reference angle is 0. So what do you draw? You basically, you imagine taking an arm and putting it here, and an arm and putting it here, and now I need to rotate that arm here up 0 degrees to get into quadrant 2. Well, 0 degrees doesn't move it. And I have to take this down, this one, I have to take this and rotate it down the reference angle, but the reference angle is 0. Degrees or rads, it doesn't matter. So what we discover is that no matter where you move it, it's the same location. This is in fact the location because it's not actually in a quadrant. We call this type of location quadrantal, which means it's between quadrants. So the answer is 180 degrees or pi radians. So first of all, have I answered your question?
Yeah.
Okay, secondly, in my mind, as soon as I got to this statement, I know that on the unit circle, cosine is x, and x is -1 in that location. So, if you're a unit circle person, then these 4 positions are not really a problem. It's when you try to work with reference angles that it gets a little wonky. Anyway, I hope that helped.
Yeah. Thanks.
You bet. Okay, so it's 2:30, everybody. The classes are scheduled for 2 hours, so started at 12:30. You are free to leave if you want. I'm still going to be here till 3 o'clock if you need help. And if you do need help, just let me know. Okay. For those of you that are going to take off, and there may be some of you, have a great day, and we will see you tomorrow. For those of you that hang around, I'll be there for help. See you, Emily.
Mr. Wei, I have a question.
Can you repeat that, please?
Sorry, I just have a question.
Of course. We'll see you, Aaron. Go ahead, Ava.
Okay, so in example 2, when we were going through it in the booklet, maybe I just missed it, my Wi-Fi glitched out, but when you were going through A, B, C, and D, you were adding 2 pi n. Why is that?
The reason I'm adding 2 pi n is because, well, let's take example A. 2a. You're okay, Ava, with the fact that these numbers that I have, that I'm going to highlight, these are the answers from question 1a?
Yeah.
Okay. So 1.02 rads, or whatever you want to call it, is this rotation angle. Are you okay with that?
Yeah.
Okay. Now, is that the only angle that ends up in that position? Well, no. Another angle, which I'm going to draw in blue, another angle, which will not be 1.02, but it will end in the same place, will be this. Does that make sense that if I rotate even further, but I go around more, I can still end up in the same place?
Yes.
Okay. So now, if I just told you, how many radians is it all the way around? It's 360 degrees, right?
Yeah.
How many radians is that?
2 pi.
It is 2 pi.
Okay.
Did you just answer your own question then?
Yeah, I think so. Thank you.
So the idea here is we are adding multiples. We are taking the small angle we have and we're adding a full revolution times some number. We're adding 1 full revolution or 2 full revolutions, but the full revolution is 2 pi. So you got it sorted out now?
Yes, I do. Thank you.
Okay, you bet. And I just want to double check. You then understand why the other ones with degrees have 360 degrees times n?
Yes.
Okay, excellent. I'm glad, Ava. You're welcome.
I need help. I'm having issues finding the second answer for 3A in the textbook.
Okay, let's take a look, Lauren. So the first thing that you do, well, you can do these in a lot of different ways, but the first thing that I would do is I would add root 3 to both sides, and then I would divide by 2. So at some point in your work, are you looking at this statement?
Yes.
Okay, good. So now there's a couple of different roads we can go down here. Did you use your calculator to find a reference angle?
No.
Did you?
I used the circle for the first one.
Okay, so use the unit circle for this one. Because you recognize that root 3 over 2 is one of those numbers on the unit circle. Now, when we say cosine of the angle equals root 3 over 2, that means on the unit circle, x is root 3 over 2. Are you with me on that idea?
Yes.
Okay, so we are looking for an x coordinate of root 3 over 2. Now, I don't know that you need to do this, but if you calculate the value of root 3 over 2, you get 0.866 something. You get almost 0.9. And on the unit circle, this is 1, which means root 3 over 2 is right here. It's a very, very large number that's almost 1. And there are 2 points on the unit circle that have that same x coordinate. Both of these points have an x coordinate of root 3 over 2. So, are you with me on that?
Yes.
So, this is why, by the way, since cosine is positive, we are going to be looking at a rotation angle in quadrant 1 and a rotation angle in quadrant 4. So what is the rotation angle? Can I ask you a question? You said you were unable to get the second answer. Did you get pi over 6 for the first?
Yes.
Okay, so that's what this is, right? So now we have to say that the other angle will be what that is. So before we calculate that, does that make sense that that's the second angle?
Yes.
Okay, so how are we going to find it? Well, just want to clean that up a bit. We are going to start counting off multiples of pi over 6. So we want to find this. Okay, so this is 1 pi over 6, 2 pi over 6, 3 pi over 6, 4, 5, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6. Don't forget, a pi over 6 is a 30-degree chunk. 10 pi over 6, 11 pi over 6 is the other angle. Now, I don't know if that's helping you out. Is that helping you out?
Yes.
Okay. So I'm just curious, were you able to identify that there were two places,
Yes.
but you just weren't sure how to find the angle?
Yeah.
Okay, so I would recommend counting off chunks of, in this case, pi over 6. You know, if the angle were here at pi over 3, then you would count off 1, 2, 3, 4, and you would continue, but they would be pi over 3s. So I hope that helps.
Okay, yes, thank you.
You're welcome. Good afternoon, Shiv. Just let me know, Shiv, were you here for the whole time?
No, I just joined.
Just within the last few minutes?
Yeah.
Okay, thank
I
you.
just got home.
Okay, how'd the interview go?
It was good.
Okay, good, I'm glad.
Yeah. I'll just.
That sounds good. Sounds good. Absolutely. Who am I speaking to?
Amy.
Oh, hi, Amy. I just didn't see the icon. So tangent equals 4.36, and we want to find solutions to that equation in decimal form in radians. So the first thing to note is, you know, radian angles sometimes are angles like sometimes angles like pi over 3 and 3 pi over 7 and those things. But those are only the cases for those special angles on the unit circle that we're familiar with. As soon as you see decimals like this, you're going to be going away from those kinds of ideas and getting decimal answers. So to start off with, we are going to find a reference angle. We have tangent of theta equals 4.36. So the reference angle is the inverse tangent of 4.36. Now, if this said, Amy, we want to find exact values, then I would recommend putting your calculator in degree mode so you recognize the numbers. But since this is decimals, we're going to just dive right into radian mode. So our calculator is going to be in radians. And we have to take the inverse tangent of 4.36. Here's the difficult thing. We get a reference angle of 1.35 radians. So theta reference equals 1.35 rads. The difficult problem is, if I told you the reference angle was 72 degrees, you know how to draw that. But 1.35 rads is kind of difficult. For those of you that are still here, this might be of interest to you. When you talk about a reference angle, it's always between the x-axis and the arm. So the reference angle can be up or down. And what that means, everybody, is reference angles are typically less than 90 degrees. Because they're small angles. Well, 90 degrees is pi over 2. And if we calculate pi over 2, you get about 1.57. What am I getting at here? I'm getting at the fact that if you labeled the angles here in rads, this is 1.57, this is 3.14. So in our question, Amy, where we had a reference angle of 1.34, it's going to look something like that. Anyway, it turns out it doesn't really matter how well you draw this. You just have to draw that reference angle in the two quadrants where tangent is positive. So I'm going to put you on the spot here, Amy. Can you take a minute and see if you can figure out for me which two quadrants have positive tangents?
1 and 3.
It is 1 and 3. So you got that figured out. That's no problem. So we're going to draw a reference angle in quadrant 1, and the reference angle is 1.35 rads. And we're going to draw a reference angle in quadrant 3 of 1.35 rads. And I didn't put units there because it's rads. Now you need to figure out what the rotation angle is in both of these cases. So can you tell me what the rotation angle will be in quadrant 1?
It will be just 1.35.
Yeah, it's just going to be 1.35. Can you figure out or tell me how to figure out the rotation angle in quadrant, if it's in quadrant 3?
Would you add 1 or 3.14 to it?
Yeah, you'd add pi. And you can actually just add pi. I said 3.14 up here someplace because I wanted to talk about decimals. But
Okay.
definitely this from, get a different color going here. This, it's not a different color. This is pi, which means that green angle would be pi plus 1.35. So my second angle is whatever that is. So now you're going to add 3.14 to 1.35 and get your answer. Does that help?
Yeah, that does. Thank you.
You're welcome. (4b), Chloe. Okay, so cosine equals negative 0.19. And again, we want this to be in radian mode. So the first step is to find the reference angle by taking the inverse cosine of 0.19. So Chloe, you too, Amy, thank you. Chloe, when we do that, we do not want to put the negative in. Even though the cosine is negative, we do not want to put it in. So I'm going to grab my calculator. I need to be in radians because we want answers in radians. I'll just double check. Yep. And the inverse cos of 0.19 gives me a reference angle of 1.37 rads. So theta reference equals 1.37 rads. Now, when we look at the actual question, Chloe, cosine of theta was negative 0.19. So which two quadrants will have cosine as being negative? Not 3 and 4. So what we do here is, so we're talking about cosine being negative. Cosine is x over r. Now, r is always positive. R is always, always positive. So where is x negative on the coordinate system? Well, this is 0, this is positive 1, this is positive 2, this is negative 1, this is negative 2. So cosine is negative everywhere to the left of the y-axis. Which means quadrant 2, which means quadrant 2 and 3. So before we go on, does that make sense in terms of the two quadrants? Okay. So now that means I have to draw this reference angle of 1.37 rads in quadrant 2 and in quadrant 3. So if I draw that reference angle in quadrant 2, I'm going to go to a bigger page. I draw that reference angle in quadrant 2. This is 1.37 rads, and in quadrant 3, this is 1.37 rads. Now, we have to try to remember something here, that that is not the answer to the question. The answer to the question is a rotation angle from 0, which would mean this is what we're after if it's in quadrant 3, and this is what we're after if it's in quadrant 2. So how do we find these? Well, we know that this is pi. If I were to rotate from here around to here, that's pi. So if I want to figure out what that green angle is, I have to take pi and subtract off that 1.37. Does that make sense before we calculate anything? Okay. On the other side of things, and we'll calculate that in a second, but on the other side of things, if it's in quadrant 3, remember that from here to here is pi. So to get the green, I'm going to have to take that pi and this time and add 1.37. So does that statement make sense to you? All right, so now it's just a matter literally of taking our calculator and figuring out what pi minus that 1.37 is. So one of our answers is 1.76, and then taking pi and adding that 1.37, 96, whatever. And the other answer then is 4.5 something. So our two answers are the 1.76 and the 4.52. Feel better about that question now, Chloe? You're welcome, I'm glad. So Katrina, I guess the answer is kind of a simple one. It depends on what you want. You're trying to find angles when you solve these equations in these questions. So if you're trying to find an angle in degrees, you want to be in degree mode. If you're trying to find an angle in radians, you must be in radian mode. Now there's an exception to that I'll talk about in a second. But for example, in question 4 here, find it, there you go. You're told that the domain is 0 to 2 pi. And what that means is you want to find angles anywhere from 0 radians to 2 pi radians. So for all of these, you're going to be in radian mode. If I go back and look at question, I believe 3, it's going to be flipping around back and forth. For the questions that I'm highlighting in yellow, even though I don't expect you to do D, since those have domains given in radians, the expectation is you want answers in radians, so you would put your calculator in radian mode. The other two that I'll highlight in blue, these two have domains given to you in degree mode, so that would mean you would want to put your calculator in degrees. Now there is an exception to that. So far does that make sense? Okay. There's an exception to that, and that's that when you want to find exact values. So I'm just going to make one up. If, in fact, you know what? A is an exception to this. And I'm going to show you why. When we take A and you rearrange this for cosine, you get root 3 over 2. Now, I just finished telling you that you have to be in radian mode for A, right? Go ahead and find a reference angle on your calculator using cosine of theta equals root 3 over 2 if you are in radians. And I'll do the same thing and we can compare answers. Do you get 0.5235 something? Okay. Now, question 3 asks you for exact values, but you can't look at that radian measure and tell me how many radians that is. But if we do this in degree mode, so even though we want answers in radians, because it's after exact values, we are going to be looking at doing this in degrees so we recognize the number. If you do the exact same calculation now in degree mode, you get 30 degrees. Now I know that 30 degrees is pi over 6. So the exact value of the reference angle is pi over 6. So I write down that the reference angle is pi over 6, but when I used my calculator, I did it in degrees so I would recognize it. So that's the exception. I hope that helps. Does that last part make sense, Katrina, that we put it in degrees so we would recognize the angle in radians? Okay, good.